All right, let's get started. So any questions, first of all? Okay, yeah, let's get started. So the last lab was uploaded, so as we said before, so that'll be a bonus lab. And so if you do it and make it all correct, then you're gonna have 3 more points in your final grade, right? Okay, so in the last lecture, we talk about, we'll continue talking about detection in the AWGN channel. And so basically we focus on how to find the base functions. And, and then we start talking about how to obtain the likelihood if we have multiple basis functions, right? So before, we focus on the case of 2 basis functions, okay? And so it just give you, to make the picture complete. So this is the example that we have seen 2 lectures ago. So basically, if we consider the case where we have this kind of waveform for S0 and S1, then we need 2 basis functions, right? So the fundamental reason is that, so this waveform and this waveform, they are orthogonal to each other, right? So basically it means that if you make inner product between this and that, and then you're gonna get 0, right? So in this case, there's no way that we only use 1 base function is enough, right? So we need 2 basis functions. In this case, we just the 2 basis functions are just like the normalized version of S0 and normalized version of S1, right? And later on, we're gonna see that. So we want to make our basis function to be orthogonal to each other, right? And in this case, so we can write down our S0 as a vector like this, and S1 as another vector, right, like that, right? So this basically means that our original signal can be represented basically by this vector and this vector, right? So basically, it basically means that if we use this value, square root of E, to multiply F0, then you're gonna get S1, right? And if you use this value to multiply as F1, then you're gonna get S2, right? So you can use, so this is a so-called vector space representation of our original function, right? It means that to use a basis function to represent our original signal, okay? So, and in this case, we can see that, okay, so the distance between these 2 constellation points is just square root of 2e, right? Instead of 2 square root of e for the antipodal case, right? So this is not as good as the antipodal case. And if we try another base function, right, and so we can write in this, the basis function in this form, right? You can double check right there. So the norm of each one is 1 still, but, and also so you can double check that they're orthogonal to each other as well, right? So in this cases, so we can write another vector space representation of our original signal, right? So which are basically S0 and S1 like this, right? In this case, right, so we have both components in each vector, right? So in this case, it basically means that, so this point represent that, means that if we use this value, multiply F0 tilde, and use this value, multiply S1 tilde, then we're gonna get our S1 of t, S0 of t, right? And if we use this value, multiply F0 tilde, and if you use minus this value to multiply S1, F1 tilde, then we're going to get our S2 of t, right? So you can see this is kind of like the vector space representation of our original signal, right? So it's really like the Fourier transform or Fourier series, right? So basically, we use all the basis functions to represent our original signal, right? Here we just see that those are another basis, right, that are orthogonal to each other. And in general, there are a few approaches to find our basis, right? So basically, we need to find a spanning set, right? So basically, a spanning set is given by this definition, right? The difference between a spanning set and a basis is that the number of basis functions here may not be minimal for the spanning set, right? So basically, we can use the functions in the spanning set to represent our original functions, right? And so we have some universal basis that we can use. For example, the Fourier series basis, right? The complex exponential, right? So that's a common thing we can use. And so in this particular case, normally we use a set-specific basis. So basically, we can use the Gram-Schmidt algorithm to compute all the bases. So it's a very easy algorithm that you can use. You can check it online. We'll see what kind of algorithm that is. So we didn't cover that in detail in our class, okay? But this is an approach that we can use. All right, so Okay, and so now we need to remember some definitions here. So basically, there are like two metrics. So one is called dimension of our space, right? So this basically is given by it basically means the number of basis functions in our basis, right? And the other concept is this number, so it's called the modulation order. So basically it means that, so how many waveforms that we're using for transmission, right? The log of capital M will give you the number of bits where we can transmit for each waveform, right? So for example, for the antipodal case, so our capital M is 2, right? Because we have 0 and that's 1, right? And in that case, we can transmit 1 bit per each waveform, right? Because we only have 2 cases of waveforms, right? And there are some, you can see that the minimum possible number of basis function in our basis is 1, right? So in this case, we have seen one example, which is the antipodal case. So actually, we're going to see that today that the PAM, the pulse amplitude modulation, is another case, right? So we only have 1 base function there. And the other extreme case is that there should be a cardinality sign here. So the maximum possible number of basis function is capital M, right? So basically, that's the orthogonal case, right? So in the orthogonal case, we have, so the S1 and S2, S0 and S1, they're orthogonal, then we need 2 bases, right? So that's the maximum number of basis function possible, right? So that's corresponding to the orthogonal case. All right, and yeah, and then want to compute how to use the likelihood function to, if we have multiple basis function, right? So we know how to compute it if we have 2 bases. If we have 2 basis functions, right? Let's generalize to the general case, right? So now we have 2 spaces. One is our signal space, and the other one is our basis space, right? So they're space of functions, right? And so here we need to introduce some notations that we use. So given SI is transmitted, then the vector of SI is given by this notation. So remember that. So this is the vector representation signal. It's a vector signal space representation of our original signal, right? And for each component here is nothing but the inner product between our transmitted signal and each basis function. Okay. So this represents each number here, right? And obviously, so we can use this number, multiply our base function, to synthesize our original transmitted signal, right? Okay, and so this is our receive structure. So basically, it's almost identical as before. The only difference here is that now we need to multiply all the basis function here, right? So before, for the antipodal case, we just have 1 FT here, right? But now we have general case, so we need to multiply all the basis function here with our received signal R of t, right? And then we do the integral, and then have our signal space representation, which is R0 to Rn minus 1, right? So yeah, without the noise, it'll be our Si, we just seen, right? But now we consider a noise, so basically we have this received vector, right? And we're going to use this received vector to make our decision. For example, we're going to see today how we can make our maximum likelihood decision here, right? And yeah, here is basically to say what I just said, right? So basically, we project RT to R, right, which is a signal space projection, and so each item in R is equals to the inner product between R of t and Fj of t, right? Yeah, here should be j instead of I. So okay, so yeah, this is the signal space representation of R. Okay, and and if we look at Rj carefully, so this is the derivation, right? So basically, after some manipulation, we can see that Rj equals to Sij equals to plus Nj, right? Where we know the distribution of Nj, right? So Nj is a Gaussian distribution with 0 mean and n naught over 2 for the variance, and where n naught over 2 is nothing but the power spectral density of the noise, right? Nt. And clearly, the distribution of Rj here should be this, right? The only difference between this and that is that now the mean is Sij, given by this instead of 0, okay? Because SIJ is deterministic, right? Because we know SI is transmitted and Fi is our base function, which is deterministic, okay? And and now, for this signal itself, Rj, so we know the distribution of it. It's a Gaussian distribution, with this mean and this variance, okay? But now, so what we want is that we want to make sure Ni and Nj, right? So basically, remember that this subscript basically means that the projection on each individual basis, right? So we want them to be independent, right? So the reason we want them to be independent is that in that case, it is easy to write down the PDF distribution or the joint distribution of all the Ris or Rjs, right? That would be easier. Yeah, because we need to use the PDF to see our decision rule, right? Okay, and in order to make them to be independent, then the only thing we need to make sure is that they are uncorrelated because they are Gaussian distribution, right? To make them uncorrelated, then we just need to compute the correlation function here, right? The expectation of Ni and Nj, right? So yeah, the reason we just need to compute that is because so Ni and Nj, the mean of them is 0, right? Okay, and in this case we can see that, okay, so if we want to if we make sure that Fi and Fj they're orthogonal, right? Then this is true, right? So basically in this case it means that they are uncorrelated, so they're independent, right? The only thing we need to make sure is that Fi and Fj they have to be orthogonal to each other, right? Which is our case here, right? If we use Gram-Schmidt algorithm to compute Fi and Fj, then we can always guarantee that they are orthogonal to each other, right? So here, this is the reason why we want Fi and Fj that are orthogonal, right? Otherwise, we don't need that. Okay, so if they are uncorrelated, we can make sure that Ni and Nj are statistically independent, right? And in this case, so we can very easily to write down the PDF of the joint distribution of R given SI set, right? So basically, so yeah, because all of the elements here Rj they are all independent, then the joint PDF is a product of each individual PDFs, right? So basically, this is how we can compute it. And then, so if we write it down, it will look like this, right? So this is the PDF function, the PDF of each individual Gaussian distribution, right? And then, so we just manipulate a little bit, right, to get rid of these two here, right? This one, this two will be canceled, and then this is what we get, right? And then, so we can see that, so basically, yeah, this product will become the summation here, right? We just multiply them all together, right? So on the exponent, it will become a summation here, right? Oh, yeah, and then, so I need to remove it. So when I copy that, I forgot to remove it, right? So from here to here, we don't have this, right? Then this is nothing but a what? Euclidean distance between R and SI, right? So this is the definition of the Euclidean distance. Okay, so basically we can write it down here. And so basically, normally we use the dr SI to represent the distance, right? So basically now we can see that similar to the binary case. So now what we get is the PDF equal to this guy, and here would be the distance, right? Remember, so for the ML rule, what do we want? We want this guy to be maximized by choosing a good I or good SI, right? So in order to make sure this guy is to be maximized, then what should we do here, right? Notice that SI is only here, right? So basically, we need to make sure the distance would be minimized, right, to maximize this guy, right? Is that clear? Right, I want to make sure the PDF is maximized by choosing an SI, right? Then equivalently, is to make sure that the distance between R and SI to be minimized. Does that make sense? Right? Then the ML rule will become a distance rule again. Okay, so this is basically what we're going to cover next. Okay. Is that clear? All right, so let's see what we're going to cover today. Okay, today we're going to continue to see the general maximum likelihood rule for multiple base functions. And then, so we're going to see spectral density. Okay, and probably we're going to end here. And the next topic that we'll be probably covering in the next lecture is the error probability. So to compute, so what is the probability that we're making a wrong decision, right? And the error probability, we're going to see that it's very related to the energy efficiency or the power spectrum, so the signal-to-noise ratio, right? Then we can see the trade-off between the spectral density, so spectral efficiency, not density, the spectral efficiency and energy efficiency, right? So this is a trade-off we mentioned when we first talking about the digital communication, right? Spectral efficiency, right? Okay, so that's the agenda. So now let's see the general ML rule. Okay, ML detection rule. So yeah, as we said before, so basically you want to pick, yeah, the rule is the same as before, right? The goal is to pick the best I or SI such that our PDF, this value, is maximized, right? So before we just have S0 and S1, right? But now we have a general PDF here, right? The derivation is exactly the same as before. Okay, so now, so given this, as we said before, so basically, so this is determined by the distance between R and SI, right? So basically, it means that we're gonna not maximize anymore, so we want to minimize the distance between R and SI. Okay, right? And as we said, so this is nothing but the distance between R and SI. Okay. So this, again, so this intuitively kind of makes sense, right? So basically it means that we're going to pick an SI that is the closest to R, right? R is our received signal, right? So basically it means that we're going to pick the closest signal, right, to R. Okay. Okay, very nice. So now let's see an example of it, right? The simplest example in this case would be PAM, right? The pulse amplitude modulation, right? Hopefully you still remember it. So do you remember what that means? Right, so basically for PAM, right, so see what we considered before is something like this, right? So for example, let's say we have a value here, and we have a value here. Let's say here's 0. And let's say we have 4 point here. This is 1. This is minus 1. This is like 3. This is minus 3, for example. And then we're going to transmit those guys. Okay? And how those guys coming from, right? It could from some kind of like quantization, right? So hopefully I still remember what does the pulse magnitude mean, right? So for example, if let's say I want to transmit a waveform like this, right? And then, so we just sample them, right? And then, so let's say we have some predetermined value here, and for each of them, so we're gonna quantize it to a certain value to transmit, right? So this is a PAM, the pulse magnitude modulation, right? Let's assume in our case, we just have 4 levels, right? We have like -1, 3, 1, 3, okay? And see how it goes. Okay, so in particular, we're going to consider 4 PAM. Okay. And so in this case, you can see that, right, all signal should be in a line, right? So in this case, can you imagine how many bases we have? 2 more, meaning 3 base functions, or 2 more signal, right? But number of base functions would be just 1 in our case, right? Because all the signal align in a line. Okay, so let's see in detail how it works. Okay, so now Si will equals to as follows. So basically, I would be from 0 to 3, right? About 4 signals, and then so this basically means this one of AI multiply G of t, where GT is our waveform. Okay, and then we have our cosine 2 pi fct. Okay, so here let's remember, so AI is our amplitude. Okay, so yeah, this is a function of I, clearly, right? And this G of t is our pulse shape, right? So this is our fixed pulse shape. Okay, and remember, so maybe the most common pulse shape here we use is a rectangle pulse, right? So that will determine the bandwidth of our signal, right? So that will determine the bandwidth of our signal, right? So you need to choose a good pulse shape. All right, and here, so it's 2 pi fct, so this guy is our carrier, right? And this fc is our carrier frequency. Right, hopefully you still remember that. Yeah, we should cover that before. Okay, so this is our PAM, and so in this case, so let's see. Let's see how we can find the ML detection rule. Okay, so in this case, let's repeat our computation before. So basically, what we're going to do is to see what is the basis, right? Because in order, to make our decision rule, so we need to figure out what is all the SI here, right? So SI is the projection of our signal on our basis. Okay, so let's compute it. So yeah, maybe let's see a little bit on why. So this would control our signal bandwidth, right? So basically, in this case, we can compute the Fourier transform of this guy, right? Let's assume SI is transmit, right? And so basically, in this case, right? So this cosine basically will just shift the spectrum, right? So basically, the entire spectrum will be determined by the spectrum or the Fourier transform of G of t, right? So basically, yeah, if so this will be nothing but our AI over 2, and then so let's assume that Fourier transform of G of t would be capital G of f, right? So then the Fourier transform of this guy will be given by G f plus fc plus G f minus fc, right? And that's it, right? So these are basically our spectrum. Okay, so basically, if we want to sketch it, it will be basically something like this, right? Yeah, so this will be our GF minus FC, and this will be GF plus FC, right? So I have a scaling in front of it. Okay, so, and you can see that if we pick a good G, and then we can determine the spectrum of our signal. Okay. And so now let's, to make our life easier, let's assume a simple G of t here. So let's assume G of t equals to Pt of t, right? Where this Pt of t is our general notation for this guy, right? So a square waveform will have 0, t here, and we'll assume here is 1, right? So this is our Pt of t. Okay, very simple, just square waveform for G of t. Right, and in this case, as we mentioned before, so all the signal will align in a line because we just use 1 of GT here, right? So basically, we can compute our basis function ft as the usual way, right? For example, we can use the normalized version of f0 of t to be our basis in this case, right? So yeah, let's keep our original assumption to make our life easier. So basically, we consider the simple case where, let's say, we have all the signal equally spaced. We have 1, 2, 3, 4 of them, right? So basically, let's assume here is A naught, here is A1, and here is A2, here is A3. Okay, and basically the value here is 1, minus 3, and 3. Okay, so this will be our signal spacing. Okay, so basically, yeah, those values are basically the value of all the A's there, right? So which is shown by this number, right? Okay, very good. And given this, so yeah, we can basically compute our basis function here, right? So basically, yeah, let's see what is our base function. So then, in order to compute our basis function here, right? So we need to compute the norm of S0, right? Let's do that. So basically, yeah, we can compute the general norm here for all the function, right? Because they have the exact same form, right? The norm of it is basically the norm square of it is basically the energy of it, right? The definition of that is nothing but we do the integral from 0 to t, and we have ai square. Yeah, and so the value here is just 1, right? So we have no scaling here. So basically, we have cosine 2 pi fc t, right? And then square dt, right? So this is a constant, right? So this should be pretty easy to do, hopefully now, right? So we just expand it by half, 1 plus cosine 4 pi fct, right? Okay. And then, the integral of that, we can assume that is 0, right? It's it depends on what t you pick, right? So normally, if S is very big, then the integral of this part would be 0, okay? Then this part is gone. Then, so we only have the first part left, right? We have a half of ai, and then we integrate that over t, right? So basically, we have a half ai squared, and then we integrate that thing over t, right? So this guy would be equals to t, right? We'll have ai t square t half, right? So that would be our value here, right? And from here, we can see that our S naught of t is equal to the square root of a naught t square here, right? So we know a naught is nothing but 1 here, right? So basically, this guy will be equals to square root of t half, right? That's the norm of S0. Then from here, so we could compute our f naught, right? So f naught is nothing but the a naught gt cosine 2 pi fct, right? Divided by this number, so which is given by this square root of t over 2, and we know a naught is 1, right? So this is nothing but square root of 2 over t gt cosine 2 pi fct, right? So this is our f naught. Okay, very good. And we know that gt is given by pt here, right? So we can replace it by pt, right? So we just write that in this way: cosine 2 pi fct pt. Okay, so this is our f naught. Okay, given naught, then now we could compute our signal space, right? Signal space representation. Okay, so let's do it here. Yeah, remember the closest, the distance decision rule. So okay, so basically what we're going to do is that, so each SI is given by SI of t, the inner product between SI of t and f of t, right? So here, or f0, call it f0, but just have one f here, right? So you can write that as f of t as well, doesn't matter. Okay, and just compute it. So by the way, so can you take a guess on what all the s's here, right? So our vector space representation S vector, right, should be equals to S0, S1, S2, S3, right? So can you take a guess on what value of each of them is? Right, because now you know f0 of t, right? Right, remember, so basically this value is nothing but, so our Si of t should be equal to what? Si multiply f0 of t, right? I think it's pretty easy to figure out what this Si is. Right, so what is S0? Right, so S0 is basically this guy, right? And this is our, so basically this is our F0 of t, right? So can you figure out what is S0 there? So you need to make sure S0 multiply F0 equal to S0 of t, right? So basically S0 would be what? This guy, right? So basically, easy to see that S0 is nothing but square root of t over 2. And how about S1? Right, S1 is when have the magnitude of A1, right? Then what is S1 there? The same, but we need a negative sign, right? Because it's -1.
But it's not squared.
No.
Because you had A0 squared. So would it be A1 squared?
What? Say again.
For S, when you take like a normal S.
Yeah.
When we calculated it, it was the square root of A0 squared times t over 2. So wouldn't it be, when we do it for A1 squared times t over 2?
No, it's not. So basically, the idea. So this is how we compute. Yeah, this is how we compute F0, right? So basically, now we need to see how to use F0 to represent our signal. Okay. So basically, for A1, so A1 is equal to -1.
Yeah, no, I got like confused with something else.
Yeah, probably it's because of my explanation, right? So basically, we use S0 to compute that, right? Then I can just move this part to the other side. But if it is A1, then we still use this F as a base, right? We don't change the base, right? That's why, so A1 is -1, then basically we need to put a minus sign there, right? For example, if we put a minus sign there, so if it's A1, then here should be a -1, right?
Yeah, my confusion was when you go back to when we first calculated it, and you have, like, take the integral there.
Here?
Yeah, you have like AI squared, right?
Yeah, this is how we compute the norm, right?
Yeah, so I thought it was when you multiply it, like, isn't this just going to be I thought it was just going to be the norm.
No, it's not the norm. It's the inner product between Si and the base function. Yes, not the norm. So the base function is now changing, right? So this is nothing but, yeah, as we listed there before. So this is this guy, right? Right. So that's always this guy, right? So then, to use this one to represent our S1 of t here, right? So because A1 is -1, then we need to put a minus sign here. That makes sense? Yeah, then how about S2? So what is the value of S2? Right, yeah, very good. So A2 is 3, right? So basically, now what we got is we have 2 times 3 there, right? It's 3 square root of t over 2, and then finally S3 should be -3. Okay, so in this case, we can directly kind of see all the value here, right? Okay, very good. And then, yeah, let's see. So basically, yeah, this is how we can so these are signal space representation, right? And pretty much it is enough. But I want to write it in a slightly more general way. So remember that before, when we talk about the orthogonal basis or the antipodal cases, we use the energy of a signal to represent all this value, right? So now this is the idea. So let's see how we can use the energy to represent all of this value. Okay, so what is what is tricky here is that, so we can see, yeah, because of different value of A is here, right? So the energy of each signal would be different, right? So this is, let's see, so this will be the energy of each signal, right? So remember, this equals to EI. So it's the energy of the signal for the ith signal, right? And we can see when I is 0 and 1, so A is 1, so their energy is T over 2. But when I is 2 or 3, then the energy will be higher, right? So then it means that we have different energy for each of the signals. So what we want is to compute the average energy here, and to use the average energy to represent the signal space representation. Does that make sense? Okay. So basically now what we're going to do is to compute the energy of it, right? So from here we can see that the energy of E0 of the signal 0 and 1 would be T over 2, right? Because the A0 and A1 equals to 1 minus 1. And then the energy of signal 2 and 3, right? So this AI square over T. So now AI is 3 or minus 3, right? 3 square over T. So that would be 9T over 2, right? Those would be the energy of those two signals, right? So now let's denote E of S as the average energy, right? So basically it means that E of S should be 1 over 4, right? Because we have 4 signals, right? And we assume that they have equal probability for transmission, right? Then we have, so this should be, we have 2 of T over 2 and 2 of 9T over 2, right? And that equals to what? We have 9 plus 9 plus 1 plus 1. So it should be 20 on the top. And the downstairs, we have 4 here, and then multiply 2. So I have 8. So that is what? 5 over 2T. Okay, so that's our average energy here, right? So now the idea is to use the average energy ES to represent this guy, right? So let's see what that equals to. Okay, so basically we can see that from here we can see if we take a square root of it, because we have a square root of T over 2 on all of them, right? So basically we can see square root of ES equals to square root of 5T over 2, right? And then from here we can see that square root of T over 2 equals to what? Square root of ES over 5, right? And then we're going to use this to replace the square root of T over 2 here, and let's see what we get. So first one is square root of ES over 5, and second one is minus of it. And third one is 3 times square root of ES over 5, and last one is minus 3 of this. Minus 3 times this. Okay, so that's basically, so the reason I want to do that is that, you know, later on when we want to characterize the error probability, so everything will be in terms of the average energy. Okay, so in that case, you know, so we don't need to specify what kind of waveform that we use or what kind of modulation, right? So we can unify all the notations in this case. All right, so given this, so now let's see how we can make our decision rule, right? So basically, we're going to draw the signal constellation. So remember, for the signal constellation, it's all these points, right? And then mapped, project into the signal space, right? So basically now, this is our signal space, right? F0 of t. So now we have our 4 points here. So after the projection, right? And our first point is this point, right? So basically we have a square root of ES, over 5, then minus square root of ES over 5, and here 3 square root of ES over 5, and here it's minus 3 square root of ES over 5. Right, so this is our signal constellation. Okay, so now let's see the distance. So basically, yeah, let's label all the S here. So this is our S0, and this is our S1, right? And this is our S2, and this is our S3. All right, and here we can see that in this case, so the distance between this guy is 2 times the distance. So let's, distance between this is 2 times square root of ES over 5, right? And so this distance is the same, I guess, right? So that is also 2 times square root of ES over 5. And similarly, you can see, so this distance will be the same. Okay, so yeah, which is nice. So it's pretty uniformly distributed. And how about decision rule? Okay, remember our decision rule is to basically to see the, so which one is the closest to R, right? So basically, the same as before. So basically, remember before our decision rule. So when we just has S1 and S0, so basically means that we find the midpoint here, right? So basically, if it's bigger than this point, it will be S0. Otherwise, it will be S1. Right? Similar here, but now we have more regions, right? So because we have 4 points here, so we're going to have 4 regions, right? So let's say, so what if R falls into this region between these 2 green lines, right? So which one should be determined, right? Which one stand if R fall in this region, right? If R is in this region, then S0 will be the closest one, right? Because remember, so this is the middle point, right? So if I'm not drawing very well, let's assume here 0. So this will be the middle point, right? Maybe let's mark it. So this would be like 2, right? 2 square root of ES over 5, and this one would be minus 2 square root of ES over 5, right? So all those are the midpoint. Okay, so basically, if R falls in this region, so you're gonna decide S0 is transmitted, right? S0 of T is transmitted, right? And if in this region, then which one will be transmitted? So if R falls in this region, so which one will be transmitted? S1, right? So yeah, S1 of T should be transmitted. And if we fall into this region, so everything on the left of this point, so basically in this case, S3 of S should be transmitted. And so basically, if on all this region, so S2 of T would be transmitted, right? And this basically, so this green is our ML decision region. Right, so before we only have 2 of them, so now because we need to determine like 4 signals and see which one is transmitted, so we have 4 regions here. Okay, so is that clear? Okay, great. So if that is clear, then let's continue talking about the spectral efficiency. So the spectral efficiency is kind of not a new concept. We didn't talk about that explicitly before, but all the gradients are there, almost. Okay, so before talking about that, let's repeat what I said in the beginning of this class. So basically, what we consider are like two important metrics. Right, the first metric is the spectral efficiency. Right, which is to measure how fast the information can be transmitted. Right, for example, let's say before we're talking about the rate, right? So it's like bit per second. Okay, how many bits per second we can transmit it, right? So here, spectral efficiency is to normalize it by the bandwidth. Okay, and the second concept is called energy efficiency, or we call that energy efficiency. So normally, how can we see the energy efficiency is that, so we normally evaluate it using the concept of the signal to noise ratio, or SNR, signal to noise ratio, or SNR. Okay, and another very important concept that we're not going to mention a lot in this class is the complexity. I say how complex we can make our decision, right? So this is a very simple decision rule, right? But in practice, we're gonna do more than that. So normally in practice, both signal to noise ratio or the energy efficiency and the complexity, so will be a function, or this will be the variable. So those would be the variable of the error probability. Okay, in other words, so the error probability will be a function of the energy efficiency and the complexity, right? So we're not going to talk much about complexity, but later on we're going to see how the error probability behave as a function of the signal to noise ratio. Okay, so yeah, that's almost the last topic in our class. All right, so yeah, let's see. So now let's talk a little bit on the spectral efficiency, right? So basically, for the idea to have this metric is that, so we want to achieve a high data rate using a small bandwidth, right? So bandwidth is kind of a very limited resource, right? So we don't want to only use a bit per second to measure the performance, right? Because that can occupy a lot of bandwidth, right? So in communication, so the bandwidth and time, they're kind of like orthogonal resources, right? We want to transmit the signal as fast as possible, and also using as little bandwidth as possible, right? This would be the idea to have this kind of metric, right? So in order to do that, let's introduce some notation here. So let's assume TS, so which is kind of our sampling duration before, as our symbol duration, right? And also, in this case, RS will be equals to 1 over TS. So that'll be our symbol rate. Okay, and for this case, for example, as this is 4-pan modulation, right? So this is called 4-RE modulation. Okay, so basically it means that every symbol or every waveform have 4 cases. Okay, so in general, so every symbol can represent can have many, many cases. So basically, in general, we have MRE modulation, right? And in this case, so the cardinality of our signal space would be equals to capital N, right? So in that case, it will be 4. Okay, so now in this case, so as we mentioned in our last class, so in this case, so every symbol or every form can represent log m bits, right? So we denote that as small m. So basically, we can transmit m bits per symbol. Okay, so for example, let's say for BPSK, right? So small m would be basically equal to 1 because we have 2 waveforms, right? And for that case, let's say for PAM, then small m would be equals to what? 2, right? Because we have 4 cases, then we can transmit 2 bits, right? 0, 0, 0, 1, 1, 0, and 1, 1, right? 4 cases. Okay, so very good. And yeah, maybe let's give you an example here. So basically, in that case, so let's say our waveform of ST or S0 of T or S0 doesn't matter because so this is a signal space representation, so they can represent the same thing, right? So we can assign 0, 0 to this waveform, and we can assign, for example, 0, 1 to this waveform, and let's say next would be 1, 0 to this, and 1, 1 to this, right? So every waveform can represent 2 bits, okay? So that will be the case. And finally, so we want to characterize the bit rate, right? So we kind of have done that before. So over time, yeah, let me write it down. So the bit rate here, R of B, so should be easy to compute, right? So this is our bit rate, right? That equals to nothing but the number of bits per symbol, right? And times the symbol rate, right? We denote that RS, which is given by this, right? Times the symbol rate. So then small m times RS will give us the bit rate. Okay? Yeah, and we only have like one more step to go to finish talking about spectral efficiency. So we're going to talk that in the next lecture. Okay. Yeah, thanks.